In this video, I want to talk about something called the determinant. And part of why I'm a little bit later than I planned on being in making this video is because it's really hard to figure out how to motivate the determinant, how to give an explanation for why we care. So in order to try to do that, I want to start by looking at an example. So I'm going to consider the matrix, and we're just going to do a 2 by 2 to make this pretty simple. But let's consider the matrix 1, 0, 2, 1. And I want to think about what this matrix does to some specific vectors. The first vector I want to look at is 0, 0. When I multiply this matrix by 0, 0, I get 0, 0. Then let's look at what this matrix does to the vector 1, 0. When I multiply this out, I get, going across the row of the matrix and down the column of the vector, I get 1 times 1 is 1, plus 0 times 0 is 0, 1 plus 0 is 1. For the second position, we're going across the second row, so I get 2 times 1 is 2, plus 1 times 0 is 0, so I get 1, 2. Then let's look at what happens to the vector 1, 1. This gives me, if I go across the row and down the column, I get 1 plus 0 is 1, and 2 plus 1 is 3. And finally, I want to look at what happens when I multiply this by the vector 0, 1. In this case, I get 1 times 0 is 0, plus 1 times 0 is 0. 0 times 2 is 0, plus 1 times 1 is 1. And so I get 0, 1. Now, let's think about what these different vectors can represent. So, if I think about 0, 0 just as a point, from 0, 0, I can represent using the first vertex, the first number, the first row as my x values, and the second as my y. I can get to the point 1, 0, or to the point 1, 1, or to the point 0, 1. So I can use these vectors to represent a square in space. Now, let's look at what happens to that square if I replace my vectors with the ones that I get by multiplying by the matrix. So my 0, 0 stays the same. My 1, 0 becomes 1, 2, which means I go over 1 and up 2. My 1, 1 becomes 1, 3, which means I'm going up another 1 from there. And my 0, 1 is still 0, 1, which means I'm getting this point here. And so my square becomes that. Now, let's think about what the area is. The area of this square is 1 by 1 is 1. The area of this is a width of 1 times a height of 1 is 1. So my area did not change. And that's the point that the determinant is going to tell us. So if you remember, we've already talked about the determinant of a 2 by 2 matrix. And to talk about the determinant of a matrix, we use the vertical lines. So I can say, like absolute value of A is the determinant of A. I can also write that as just determinant of A. But I can also use, if I don't want to specify, I can just replace the boundaries of my matrix with, instead of square brackets, just with vertical lines. And this says the determinant of that matrix. And we've talked about the determinant of a 2 by 2 matrix already. And to get the determinant of a 2 by 2 matrix, you take the, you multiply the numbers on the diagonal together. So 1 times 1 minus the numbers on the off diagonal. So 0 times 2. And that's equal to 1. And so what happened to our area? Well, it stayed the same because the determinant was 1. If I used a different determinant, or sorry, a different matrix, like say 2, 0, 0, 1, then I would get a slightly different set of vectors. That looks like this. And if I plot those out, I'm getting my 0, 0. Then I'm going to 2, 0. So I've gone wider. And then I'm going to 2, 1. And then I'm going to 0, 1. Which has a area of 2 times 1 is 2. And if I look at the determinant of this new matrix, I get 2 times 1 minus 0 times 0 is equal to 2. And so the determinant tells us how much that area is going to get multiplied by. So that is one of the things that the determinant tells us, and that's how I want to motivate it. Now, that's not the thing that will be most important to us about determinants. One of the things that will be really valuable for us is that the determinant is going to tell us whether a matrix is invertible or not. But we're going to get to that in a second. So we know how to find the determinant of a 2 by 2 matrix. But I want to go a step back and think about the determinant of a 1 by 1 matrix. So if I have some matrix that's just a single row and a single column, well, we just call the determinant the number inside the matrix. It's the best we can do. Now, if I have a 2 by 2, let's do it completely in general. We know how to do this, right, already. It's A1, 1 times A1, 2, 2 minus A1, 2 times A2, 1. But I want to think about this in a slightly different way. I want to think about this as going across the top row. So I've got the first square is A1, 1. And I'm going to be multiplying that by whatever's left after I cross out the row and column that includes that first square. So that's multiplying it by A2, 2. Then we'll do the same thing going to the next thing in the first row. A12. If I cross out the row and column that includes A12, I'm left with A21, and I'm going to subtract A12, the row and column that I'm picking and removing, times the remainder, A21. And this is the basic idea we're going to be doing. And it doesn't matter which row or column you pick. You're just going to be going across a row or column and multiplying by what's left after you remove that row and column. So let's see this with a specific example. Let's see this with, say, a matrix like 1, -2, 5, 0, 2, 0, 4, -1, 3, 1, 0, 7, 0, 4, -2, 0. And if this is our matrix A, I want to define A, say 3, 2, is going to be the matrix that is produced by crossing out the third row and the second column. So A32 is going to be 1, 5, 0, 2, 4, -1, 0, -2, 0. And so to find the determinant of a matrix, what we're going to do is we're going to go across a row or down a column. It doesn't matter which one you do. So let's say we want to find the determinant of A. I'm going to pick a row or a column. Let's pick the third row. And I'm going to do 3 times the determinant of A31, because that's the 3, because that first number, the first column, first row is 3, times the determinant of A31 is whatever is left out, minus 1 times A32, the 1 because that is the entry in A32 in the third row, second column, plus 0 times the determinant of A33, minus 7 times the determinant of A34. Okay, so there's a lot of addition and subtraction and things like that. So let's see if we can figure out how to keep track of those. So what we do to keep track of those is, if our matrix A is this 4 by 4 matrix, then we think about another matrix that's 4 by 4, not technically a matrix, but you'll get the point. And we start by putting a plus sign in the upper left-hand corner. And then we just go and make a grid so that we have a checkerboard pattern of plus and minus. And so if I'm going across a row or down a column, I pick which one I'm going to do. So we chose that third row. So I'm going to take 3. That corresponds to a plus. So I'm going to take a positive 3 times the determinant of that piece. Then I go to the next number in that row. That corresponds to a minus. So I go minus 1 times the determinant of the remainder of the matrix. Then I go to the next one. That corresponds to a plus. 0 times the determinant of the remainder of the matrix. Then I go to the next one, minus. So minus 7 times the determinant of the matrix of after I cross out that row and column. And this process will give you the determinant. This is called cofactor expansion, and we call these the determinants of these matrices that after we cross out a row and column are called cofactors. And so this is how we can calculate a determinant. However, this is a very bad way to calculate a determinant. And the reason this is a very bad way to calculate the determinant is because in general, this takes a very, very long time to do. When I was taking my linear algebra class as a student, I had a, at the time, brand new calculator that was one of the first ones that could take a determinant of a matrix for you. And my professor told us how long this would take and to do in general. And so I plugged into my calculator in a way that required it to use cofactor expansion because I didn't use any numbers. I only said, okay, now just use all these different variables and give me the determinant. And when I tried a 4x4 matrix, it took the calculator about 5 minutes. I tried a 5x5 matrix, and the calculator ran out of batteries before it finished. So it is, and it probably took less than 5 minutes for the 4x4. It probably just 20 seconds or so, something like that. But it was long enough that it was taking some time, but it wasn't a long wait. But as soon as I got to 5x5, the calculator couldn't do it. So we need better ways to determine the cofactor, to determine the determinant than the cofactor expansion. So I want to look at a specific type of matrix that will make it a lot easier if you can get it to this type of matrix. So if I have a matrix that looks like, doesn't matter whether it's upper or lower, but a triangular matrix. Say 1, 2, 3, 4, 0, 2, 7, 1, 0, 0, 1, 8, 0, 0, 0, 3. Something like that. If I want to take the determinant of that, I'm going to use this last row or the first column. It doesn't matter which. Actually, let's use the first column. I'm going to use the first column. So I'm going to start with 1, and that's a plus. Then it'll be minus, plus, minus, etc. So this determinant is going to be 1 times the determinant of 2, 7, 1, 0, 1, 8, 0, 0, 3. Minus 0 times some determinant plus 0 times some determinant minus 0 times some determinant. These don't matter because I'm multiplying by 0 for each one of them. So now I've got 1 times that determinant, but that determinant is a upper triangular matrix again. So I can go down that first column and get to calculate that determinant. It's 2 times the determinant of 1, 8, 0, 3 minus 0 times some determinant plus 0 times some determinant. Those pieces don't matter because they just go to 0. To calculate that determinant, though, I get 1 times 2 times 1 times the determinant of 3 minus 0 times the determinant of 8. That piece doesn't matter, it goes away. So my final determinant is 1 times 2 times 1 times 3 is 6. So if I've got some upper or lower triangular matrix, all I have to do is multiply down the diagonal. So if A is a triangular matrix, then the determinant of A is the product of the entries on the diagonal. So that's the first piece of information I want to point out to get to a faster way of taking a determinant. But this really only works if you're upper triangular or lower triangular. So this is only helpful for a very specific set of matrices. So the next thing I want to think about is, let's go back to what the matrix does. The matrix preserves the area of anything that we build by enclosing it with vectors. So if I build say a triangle with three vectors, x1, x2, and x3, then the determinant of the matrix will tell me how much I'm changing that area when I go to A1, A2, A3. So if I think about that, and I have, say, another matrix B, and I take B times A1, B times A2, B times A3, that's going to give me some B1, B2, B3. And so if I think about what's going on, the area enclosed by the B1, B2, B3 is just the determinant of B bigger than the area enclosed by A1, A2, A3, which is the determinant of A enclosed by x1, x2, x3. So if I think about the matrix BA, x1, BA, x2, BA, x3, what that does is it gives me BA1, BA2, BA3, which is B1, B2, B3. And what has happened to the area is we have taken the area of x1, x2, x3 and multiplied it by the determinant of A, and then taken that area and multiplied it by the determinant of B. And so what that means is that the determinant of B times A has to be equal to the determinant of A times the determinant of B. So what's important for us is when I multiply matrices, the determinant of the multiplied matrices is equal to the determinant of the matrices multiplied together. I can separate out that determinant to do it in a different order, take the determinants one at a time. Which means if I can come up with some way to multiply some matrix A by some other matrix, let's call it B, and for us, for this purpose, the order doesn't matter because I can flip these are just scalars, so I can flip those orders. So if I can take the determinant A times and get the determinant B this way, A times B like that, then I know that this is the determinant of A times the determinant of B. And so if I can figure out nice, easy to work with determinants of matrices that will multiply together to get me what I want, I can build my determinants by coming up with these ways of getting to the matrix I wanted to be at. That was poorly said. Let me say it again. If I can replace the matrix C that I'm interested in with the matrix AB when I take the determinants, so if I can write that C is equal to A times B, then to calculate the determinant of C, all I have to do is calculate the determinant of A times the determinant of B. And so if I can find determinants of matrices that multiply together to get to what I want, I can use those easier determinants. And it turns out there's some really nice determinants that will make this, some really nice matrices that will make this work very well. We call these elementary matrices. And so elementary matrices, if we think about reduced row echelon form or row operations, we have 3 row operations. The first one is we can swap rows. The second is we can scale a row. And the third is we can add a multiple of one row to another. Well, all of these row operations can be done through elementary matrices. So to swap rows, if I want to swap, say we're working with a 4x4 matrix, if I want to swap row 2 and 4, what I do is I take my identity matrix and I swap rows 2 and 4 in that to get this matrix. This is our elementary matrix that represents swapping rows 2 and 4. And if I take E, this elementary matrix operation, times any 4x4 matrix A, what I get is A with row 2 and 4 swapped. And I can do the same thing to scale a row. So if I want to scale row 3 by 2, for instance, I just use my identity matrix, and I scale row 3 by 2. And multiplying this E by A will give me A with row 3 scaled by 2. And the same thing for adding a multiple of one row to another. So if I want to add 2 times row 1 to row 3, well, my elementary row matrix, or my elementary matrix, would be 2 times row 1 gets added to row 3, so that gives me 2, 0, 1, 0, 0, 0, 0, 1. And each of these elementary matrices have very easy to calculate determinants. So the determinant involved in an elementary row operation that involves a swap is -1. No matter which two rows are swapped, that will always come out to be -1. The the determinant of the elementary matrix that corresponds to scaling a row will be the factor that we scaled it by. So because you can just multiply down the diagonal, because this is a triangular matrix, that would be 2. Or it's whatever that scaling operation is. And this is a little bit surprising, but this last one, no matter what multiple of a row you add to another row, the determinant of that row, of that elementary matrix, is 1. What this means for us is if you want to calculate the determinant of a matrix in a more efficient way, you can take any matrix A and reduce it to echelon form. Keep track of all the swaps you did. Keep track of all operations you did. And for every swap, you will be multiplying by -1. For scale changes, multiply by the scaling factor. And for adding a multiple of one row to another, you can do nothing. And this will help you to calculate the determinant of a matrix. Let's look at an example. Let's do a 3 by 3. So I'm going to do 1, 2, 3, 2. Actually, let's do -2, 1, 7, 2, 4, 1. So to calculate this determinant, all I'm going to do is get this into a row echelon form. In fact, I'm going to change. Yeah, we'll do it this way. I'm going to get this into row echelon form, and then reduce it to where at least down the diagonals, it's all 1s. Or actually, I don't even need to do that. We're just going to go into echelon form. So to do that, I'm going to add 2 times row 1 to the second row. When I add 2 times row 1 to the second row, I get 0. 4 plus 1 is 5. 6 plus 7 is 13. And add -2 times row 1 to the third. That gives me 0, 0, and -6 plus 1 is -5. And all I have done is I've multiplied by one row by another. So I have changed my determinant by nothing. Now, I'm going to scale Just to illustrate it, I'm going to scale the second row by 1/5. If I do that, I get 1, 2, 3, 0, 1, 13 fifths, 0, 0, -5. And I've multiplied by 1/5. And so, if I want to think about what I've done to the determinant, well, this determinant of this is -5, and I multiplied by 1/5 to get there. So the determinant of here was -25, and I made no changes, so that my original determinant was -25. And I can calculate that a lot faster this way than by using cofactor expansion. Okay, so this is how we calculate a determinant. I want to talk about some properties of determinants. So we've already talked about what happens with row operations. What is really important for us, maybe the most important thing for us, is a square matrix A is invertible if and only if the determinant of A is not equal to 0. But we can go a step further than that, because the determinant of A inverse is equal to 1 over the determinant of A. So if it is invertible, if the determinant is not 0, then I can calculate the determinant of the inverse just by taking 1 over that value. We can go a step. We can also say that the determinant of A transpose is just equal to the determinant of A. Transposing, because rows and columns, you can go down a row or across a column. Down a column or across a row. It doesn't matter which one you do. Transposing doesn't change anything. And I think that is all of the things that I wanted to talk about for this video. So that is the basics of matrix determinants. And the biggest, most important thing that we do with a matrix determinant is the idea that if the determinant is not equal to 0, then the matrix is invertible. The idea of cofactor expansion will work in general for any matrix, and you can use row reduction to calculate a matrix determinant much more quickly than through cofactor expansion. And I will see you guys next time.